Okay, there was something, there were a few things here. Okay, so as mentioned, I did post, but just now, sorry, I can't go into student mode because I want to show you something, but I posted these chapter 2 combinatorics, which are just mine kind of highlights of chapter 2 that we're going to be following along with. In case that wasn't clear last week, first page, I didn't highlight anything, but then everything that I want to talk about, I highlighted here. And so we'll work our way through these today. The other stuff in there is obviously important and might be helpful if it's not clear what I'm saying, right? Then they explain it more around those points, but they're mostly for me to remind myself what to say and do. But I did want to show you that I posted an assignment because I can't remember if I talked about it on Friday or what. Anyways, doesn't hurt to say it again. Well, I think I did. I'm having a vague memory. I did, right? Vague memory of a Friday due date versus Sunday due date discussion. We landed on Sundays because it's no difference to me. I like to do Fridays because then you guys are free for the weekend. And isn't that so nice of me? But we decided on Sunday, but obviously you can set your own personal due date for Friday. But anyways, there's just an assignment on chapter 1. It was kind of, and this is where the marks will come from, obviously. So that's due Sunday. All right. Was that all I wanted to say? And now I feel bad because my morning classes, I feel like get me all fresh and I remember everything. And then by the end of the day, like, did I say this already? Did I do this? I try to post a little thing on the calendar to remind you, but I will say that they're not linked in any way. So this is just kind of, I put that on there to help you. But if I say that I'm going to change a due date, which I'm open to doing, if you have other, the collective you, all of you as a group have many due dates, and just ask me, hey, we've got all these assignments piling up. Can you extend your due date? Then I'm happy to do that. Unless there's a test, then obviously I want you to do the assignments before the test because they're meant to help you prepare for the test. But if you click on it, then this is the due date. That's the real due date. Okay. So that thing in the calendar, just so you know, because it can be confusing. Oh, it still says it's due on Sunday, but she said it was going to be due on the Tuesday or whatever. Who cares? Then just go in here. This is the one that matters. If I haven't changed this one, then you can send me frantic texts and emails. Okay. Then I need to do the extension. Yeah. All right. Cool. And it's just a little shorty assignment, I think. But now, I shouldn't have said that because I don't actually remember. But I feel like it was a short assignment. All right. So let's see here. Chapter 2, Combinatorics. I'm feeling like I forgot something, but I'll sprinkle it in as we go, I guess. I don't know. What's combinatorics? Combinatorics is essentially counting, right? Which sounds kind of ridiculous, right? But it's essentially counting. Counting can be quite sophisticated though, right? How many ways can I have a full house from a deck of cards, for example, right? That's counting. how many ways can I do this? How many ways can I do that? Right? And so counting can be quite sophisticated. Luckily for me, because I don't like combinatorics, we're not going very deep at all. So even though I'm in stats, so combinatorics is part of stats, probability, all that kind of stuff, but it's not the part that I like. So you can't like all of it, but you have to like some of it. Okay. So combinatorics, what is it? Blah, blah, blah. It's counting. So for example, how many lunches can you have? A snack bar. Doesn't that sound fun? Serves 5 different sandwiches and 3 different beverages. How many different lunches can a person order, right? You have to have a sandwich and you have to have a beverage, and there's no other options. Okay. And so what are some of the things that you're maybe checking off in your mind? Well, so you have to have 1 sandwich and you have to have 1 beverage. That was one thing that we had to kind of check in on. Yes, in this case, that's true, right? Can I just grab 2 sandwiches? No, right? Because then it changes everything. What about nah, let's just leave it there. It's gonna go a little crazy. But I'm getting ahead of myself. Okay. So without any of this, right? If the question just ended here, how many different lunches can a person order? What I want you to do is just kind of take a step back and think about how you would tackle this problem. Now, there's a giveaway here, right? You could do it kind of methodically with a tree diagram, right? And that's usually how we do these counting problems, as long as they're not terribly large, okay? But there are many ways of solving this problem. And I think that's why I don't like combinatorics so much, is because there are many ways to get to the same answer, as we'll see. And so that's fun and all, but it's hard to kind of get down and remember one way that's going to work always, because that's not the case. Okay? And maybe that's where I struggle with it. I'm having an epiphany. Maybe that's what's hard for me, right? I like to just have one way that's always going to work, even if it's a little bit more tedious, but that's just me. Okay, so one way that you could go about it is to say, all right, first I'm gonna grab a sandwich, right? And so then I have 5, and they've even gone through the trouble of naming the different sandwiches. Bologna, ham, cheese, chicken, beef. Fine, I'm gonna take a ham sandwich out of these 5 choices, right? So I had 5 choices, I have to pick one. I'm gonna grab a ham sandwich. Then I have the choice of beverage, milk, coffee, or tea. And no milk in your coffee or tea, I guess. You can only have one. So you have to get a friend who gets a tea and you get the milk, and then you share them, I guess. Whatever. Right, and so here now I have 3 choices. Regardless of which branch I went down here, right, I'm still gonna have 3 choices. And so what this ends up being is just a multiplication problem. Okay, and here, right, we can list all the possible outcomes, right, by just listing the branches that we went down. Okay. So we weren't asked to list all the possible outcomes, but on the flip side, if we're able to list all the possible outcomes, then you can just count them, right? And so it is counting still. Okay. we see that there's 15 different combinations, as you might have been leaning towards, right? If I have 5 sandwiches that I can choose from, and I have to choose one, right? And then I have 3 beverages, three beverages to choose from, right? And so then I have 5 times 3 possible combinations, right? And so 15 different lunches can be ordered, right? And so there are lots of different ways of getting there. And we're gonna learn some tools today. I always like to just go through it, very tedious, but I like tedious things because it makes me feel like I'm really good at doing them. Well, I am really good at doing them if I've done them a lot. Okay. We were talking about Cartesian products last day. This one's kind of worth having a look at, even though I haven't highlighted it, right? So if we have a set of A, B, C, D, E, and a set 1, 2, 3, okay, we can look at the Cartesian product. And what did we say? We said, okay, the Cartesian product, we can find the cardinality by multiplying the 2 cardinalities, right? And so here we said we have 5, we could call these sandwiches, A, B, C, D, E, that's boring, right? And 3 beverages, right? I'm picking from a set of sandwiches and a set of beverages, right? One has 5 elements, one has 3 elements. So the cardinality of the Cartesian product of the 2 is going to be 5 times 3, 15. 15 possible elements in the Cartesian product. Yeah. And this isn't obvious the first time around, right? When you're doing these problems, these counting problems. And so I encourage you to, if you haven't already, just kind of read through the examples and work through them. But I'm going to skip ahead a little bit to the rule of products. So like I said, this is really just a multiplication problem. Multiplication is a product. Okay. So if 2 operations must be performed, right? You have to grab a sandwich and you have to grab a beverage, okay? And if the first operation can be performed P1 different ways and the second operation can always be performed P2 different ways, then there are P1 times P2 different ways that the 2 operations can be performed. Okay? And so one really important thing here is that the second operation can always be performed P2 different ways, okay? Which is another way of saying that, okay, well, P2 can't depend on, or P2 cannot depend on what you did for P1, right? The beverages that are available to you are not allowed to depend on what sandwich you grabbed. Oh, you grabbed a beef sandwich? Well, then no milk for you, right? That can't happen. We can handle that, but we're not going to get there in this course. You'll have to take a stats course, right? Rats. Or you can just Google the rule of products for dependent events and get there. So what we're saying is that P2 does not depend on the option that's chosen in the first operation. Okay, so P2 is independent of the first operation, or on the flip side, they can be dependent on each other, right? Or one on the other. If that's the case, though, then the rule of products no longer applies. There's a little example here, right? Which is basically what I said. So assume that coffee is not served with beef or chicken sandwiches. So knowing that you grabbed a chicken sandwich, which is kind of weird anyways, then no coffee, right? But then it would reduce the number of possible outcomes, right? And we can't use the multiplication property anymore. We can obviously extend this to any number of operations, not just P1, P2. We can extend it to Pn operations. Now, maybe this is a good time. Okay, sure. Sure. How I think of these operations, and for me, this helps. If it doesn't help, just ignore it. But each operation I think of as just a blank line. So here I have operation 1 and op2 and op3. Right? So each little slot is for operation 1, operation 2, operation 3. And then what I do is I put the number of options that I have for each operation above it. So the number of options in op1, maybe there's 3 options. Maybe there's dessert, operation 3. We can do that. Maybe there's, how many desserts do we want? 2, because I can't multiply 15 by anything more than 2, just on the spot. I can, but I don't want to. 2 desserts. So 3 is the options. Oops. Options in 2 and options in 3. Wow, that's confusing. 3 is the number of options in 2 and 2 is the number of options in 3. That's terrible. How about we make it 4? If I can double it, I can double that and double down. Right? Because what am I going to do here? To find the number of possible combinations, right? Then I'm going to multiply through, and I've run out of room here, but this is the number. Which is what? 5 times 3 is 15 times 4. That's where I went to 2 to get me to 30, but then I can do that times 2 again, get me to 60. If we add a dessert. That tree, if you imagine the continuation of that tree now, right? Each of those beverage branches would have 4 branches coming off of it, and now all of a sudden it's huge. Right, so those trees are only really useful if you have very few options that you're looking at. It's a nice way to kind of, you don't have to map it out exactly, but to visualize it at least. And now I'm having that moment where, did I record? I did. Oh, phew. Okay. Things like a multiple choice questionnaire or multiple choice quiz. Right? How many possible answer combinations are there? Even if you only have, is that me?
Oh, that's me, sorry.
Oh.
Yeah, notification.
Like, hello? Hello?
I don't know how to silence this up.
You can just mute it.
Yeah.
So popular. So if you have 4 questions that have 2 possible answers, and then 3 questions with 5 possible answers, okay, then it doesn't matter what the answer was to the previous question. Let's assume they're all independent of each other, right? Then how many different ways do we have to answer this questionnaire? Now, this is where I like to use those kind of, I don't know, I think of them as slots. If I have question number, okay, yeah. Question number 1, 4 questions, 1, 2, 3, 4, with 2 possible answers, right? 4 questions that have 2 possible answers. The important part is reading the question properly, right? 1, 2, 3, 4 all have 2 possible things that I could choose from, right? Then 3 questions with 5 possible answers. So 1, 2, 3, so 5, 6, question 5, 6, 7 have 5 possible answers. And then to find the possible, all the ways that we could get answers, assuming that we have to answer all of the questions, right? Whether right or wrong. Yeah. And let's do this, is 2,000. I mean, they've done the math for you there. So 2 to the power of 4 times 5 to the power of 3. Let me ask you this. Does it matter that I listed question number 1 as having 2 options? What if it was one of the 5 options? No, right? Because 2 times 2 times 2 times 5 times 2 times 5 times 5 is the same as what we wrote there. I might have missed a 2 or a 5 or both. Right, but the idea is there, right? So the order in multiplication doesn't matter, right? And so we're just seeing how many different ways we could have 4 true false questions, let's say, and 3 5 answer questions. Multiple choice words. Okay, so what's the take home here? Order of questions doesn't matter. Right. I actually thought I didn't include, because I find this kind of condescending. Do not underestimate the usefulness of simple ideas. Well, no, doy. But I guess I put it in the box. Sorry, guys. Last week we talked about the power set of A. So we were talking about sets, and then the power set of A is the list of all possible subsets of A. We talked about proper subsets, improper subsets, all that kind of stuff. And so the question now is, can we predict how many elements are in the power set of A for a given finite set A? Okay, so A has to be finite, but if it is, then if it has cardinality n, which it must if it's finite, right? It can't be infinite. Then the cardinality of the power set, just as a fact, is going to be 2 to the power of n. That's super useful in scenarios where you're asked to list the power set, right? Well, how many am I going for? right? And then you can start checking them off. It doesn't tell you what they are, right? But it tells you how many there are, and then you know that you can kind of check it that way. And so they do the proof. I'm not really big on doing proofs in class. We do have to do logic, so we'll do enough proofs, but this one's relatively simple, so fine. If A is a finite set, then the cardinality of the power set of A is 2 to the power of the cardinality of A, which is what we just said, and I highlighted it, and we said, oh, that's nice to have in our back pocket. But here's the proof. So if we let B be any subset, so any element in the power set, right, then as long as A has cardinality n, okay, then any element X is either in the subset B or not in the subset B, right? It's all in A, and if I'm making a subset, a generic subset out of A, then this generic X could either be in this subset or not in this subset, right? Because it's a subset of A. And so what we have is for each element, we have 2 options. You're either in the subset or you're out of the subset, right? And so what we end up with is this 2 to the power of n. Now, I'm feeling pretty confident about this, but I did add, there were no cardinality bars around the power set of A. But like I said, I'm feeling pretty confident that they should be there because it doesn't make sense otherwise. But just so you know, if it comes back to haunt me, should I email the authors? I'm not going to. I never do. There's typos everywhere. Not in this book. This book's relatively good. But I did add those on, so I guess just kind of word of caution. Right. There are some typos. Okay, so that's kind of a warm up to counting. And a lot of counting can be done with just that multiplication rule. I think we call it the rule of products. Call it the multiplication rule sometimes. They're all the same. So there are some exercises. I think not too many in this section, but these are the ones that we'll go through on Friday. I'll be better about posting the solutions. Maybe I'll even start tonight. I don't know. Probably not. It's been a very long day. But we'll save those, right? Because what I want you to do with these exercises that are highlighted, I mean, you can do the other ones if you want to, but I'm only going to do these. Just go through them and then check against the solutions, and then we'll go through them or a subset of them on Friday. Can't do all of them. That's crazy. I was thinking one of the options instead of a Friday, well, not really instead of a Friday class, was if I recorded myself, but then it's just me thinking, solving the problems. And then you could watch that video. But I think it could be a little boring. But I could do that as well. And then you could have the whole video. It'd be hours of me solving problems. Just talking to myself. Maybe not hours. Well, 2 at least. 3 maybe. I'm pretty slow. Okay. So special case of counting is called permutations. And so permutations are when the order matters. Okay? And so what happens is if we have, and we looked at, and I like these examples because they tie into last week really nicely. But if you have a set A, B, C, then how many different ways can we order the three different elements of the set A, B, C? Right. Now, with permutations, what happens is once you've used something, right, A, for example, you can't use it again, right? And so the number of options keeps dwindling down as you go, okay? And so that's kind of the tricky part. But so what it looks like is if I pick A, then the second letter I have to pick from is either B or C, right? And if I chose B, then the third letter must be C, right? If I pick A and then I pick C, my third letter has to be B, right? And so I'm at each increment, I start out with three options, A, B, C, and then I end up with two options and then one option off of each branch, right? Which means in terms of kind of my slots here, I'm curious to know, this is how I was taught with these slots. And I will say they didn't make sense in the beginning, but now I use them quite a bit, obviously. And so my first option out of A, B, C, I'm just trying to figure out how many ways I can reorder these things, right? And so for my first slot, I have three options, right? A, B, C, right? Well, I shouldn't have done that because now I have to subtract sets. Fine, I'll leave it for the one. How about the second one? So now I've used up one of those letters as the first letter, right? I'm not specifying which one because it doesn't matter, but now I only have two letters to choose from, right? Regardless of the branch that I went down to reuse letters. If I was allowed to reuse letters, then that's great, right? Then I could do that and we would still have three branches, but that's not the case, right? For this slot, I only have one option, right? It's determined by the previous two. Yeah. So in terms of how many different ways that I can order these things, well, then I just multiply through here. 3 times 2 is 6 times 1 is 6. So it's kind of addressing two different questions here. Here we see the different permutations, right? See the different ways that I could arrange three letters, okay? And here I'm just counting how many ways I can arrange them, right? It's not telling me what they are. But knowing that there are 6, I think it's easier to get there, right? You'd start with the obvious A, B, C, A, C, B, B, A, C, right? And so on and so forth. So you don't need to use a tree diagram, but I find that they are nice for visualizing things. In terms of terminology here, each of these 6 orderings, so each of these unique orderings is called a permutation of the set A. I didn't highlight this one, but it's kind of cute. So a student is taking 5 courses in the fall semester. How many different ways can the 5 courses be listed? Right. I guess on a schedule or something like that. It wouldn't make sense to list the same course 5 times and then the other ones are just secret, I guess. That doesn't make sense, but you can order them alphabetically or by time of day or by instructor last name. There's lots of different ways that you could order them, right? And there doesn't have to be logic behind it. But how many different ways can we list these courses? First course, I've got all of them to choose from, right? I've got 5 things I can choose from, 5 courses. That's a full load is 5, right? 5, 3 is the cutoff, I think. That's fine. It doesn't matter. I'm mostly curious. But then once I've listed that course again, it doesn't make sense to list it twice, right? So now I only have 4 options, right? Once I've listed that, whatever it is that I chose, right, it's removed from the options, and then it just keeps going down and down and down until I'm left with just the one option that I haven't listed yet for 120 different permutations of the set of courses. So what we're seeing, right, or what's important is we're arranging things from a single set, right? And so we can't make a list of multiple students at once, right? We're just talking about one student's courses, right? And each element is listed exactly once in each list, right? Again, no double counting. So if there are n choices for position 1 in a list, then just generically, and we're going to rely on this quite a bit. So if there are n options to begin with, then what happens? N minus 1 options, n minus 2 options, all the way to 2 options followed by 1 option, right? And from here, it should be kind of obvious what that's doing, right? It's decreasing by 1 until suddenly you've decreased so far that you only have 2 items left, and then finally 1 item left. Oh, okay. And we're multiplying between here. Yeah. But Emily, that looks like the factorial of n. It is. You guys seen n factorial? Oh, maybe not. No. N factorial, really n? Because it's an exclamation mark. But no, so this is what n factorial is. It just takes, it starts at n and then multiplies by all the numbers that are greater than 0, but less than it. Okay, so for example, 5 factorial would be 5 times 4 times 3 times 2 times 1. Let me just scroll ahead a tiny bit to make sure. Okay, I'm not jumping ahead too much. Oops. What are some things I could do if I wanted to kind of get fancy? Or I could write 5 times 4 factorial. That's still true, right? When would that be useful? Maybe if I had something like 4 factorial divided by 5 factorial. Why would that be useful, being able to rewrite 5 factorial as 5 times 4 factorial? because I'm multiplying 5 times 4 factorial. Since I'm multiplying, I'm allowed to cancel these, right? And I'm just left with 1 over 5. Womp womp. That's really small. Usually, I guess we'd cancel on the top, but I'm just winging it here. Okay. So you can always kind of truncate wherever you want this factorial, right? Because 5 times 4 times 3 factorial, 3 factorial is just 3 times 2 times 1, so it just keeps going, right? It's really useful in simplification is when it comes in. Oh yeah, baseball team. Kind of fun. Turns out, well, I don't know anything about baseball, so for me, they're all over my head. Although they're just math examples, but it does talk about, you know, we can have different ways of ordering things, right? Some of them make sense, alphabetical, all that kind of fun stuff. And some of them don't. Okay? But they still exist. Student numbers, all that fun stuff. So here's a little block on the factorial. If n is a positive integer, right? Notice how we're using this terminology just right away. Now we're just expected to know what an integer is. An integer is a whole number, right? But here it's a positive integer, right? So that's fine. Then n factorial is the product of the first n positive integers and is denoted by n factorial. I don't know how else to read it, except for really n, but that's not true. One thing to keep up your sleeve is that 0 factorial is just defined to be 1. Okay? It doesn't make sense, but it's true. It's a fact. Zero factorial equals 1. And I'm sure there's a proof somewhere, but I've always just surrendered to the fact. I haven't looked that deep into it. It makes sense, though. You can't just go 25 factorial and then you get to the end 0 times 0. It's always 0. It doesn't work, right? And so that's probably why. Okay. And here it's just emphasizing that 4 factorial is 4 times 3 factorial and just kind of shows you that you can use it for simplification, right? And so if you find an answer of 25 factorial over 23 factorial, right? Let's just jot that down on the side here. 25 factorial over 23 factorial. Well, I'm going to try to simplify by canceling with the smaller of the 2 factorials, right? That's what I did previously. And that's what I'm going to do again. And so now I'm going to have 25 times 24 times 23 factorial. I can stop there because I've reached my destination. Now I can cancel 23 factorial, and all I'm left with is 25 times 24, which is, I guess, 600. Okay. So there are going to be times when you're working with very large numbers in the form of factorials, right? So even 7 factorial is 5,040, right? And so, and 25 factorial is whatever this monstrosity is. I don't think, Well, now I'm curious. Can your calculator handle it? I don't think so. I think mine's going to clunk out. 25 factorial. Where's the factorial? I know I have one. I do. Okay, so it did do it. Wonder what the max is. Anyways. If you have a calculator, something like this, most of them have a factorial button. So you can find it. Mine was in the second menu. Might be helpful. But Emily, when would I possibly use that? Well, if the cardinality of A is n, then there are n factorial ways of permuting all n elements of A, right? So, which makes sense. If you think about the slots, right? If I have n elements, I have n slots. For the first slot, I have n options because I can choose from all of them. Second slot, I have n minus 1 option because I already used one. Third slot, I have n minus 2 options, right? And so it becomes n factorial. Let's see here. So here, if we have n elements, right, n slots, then I have n choices initially, n minus 1 choices, down to, I'll just do 1. Because it should be relatively clear, which is n factorial. Notice that so far we've only talked about, okay, how can I rearrange all these letters, right, from the full set? What if we wanted to only talk about a subset, right? So what if we only have, or what if we only care about k elements out of a set of n objects, where we have to say that k is less than or equal to n because I can't grab a subset of size 5 from a set of 4, that it can't be, right? And so now, right, and we played around with this last day where we said, okay, given these 4 elements, how many possible subsets of size 2 can I have, right? Size 3. That was a little bit more work, right? And so we've already done this, but now we're going to have a formula for it. So we want to permute k elements out of a set of n objects, which leads us to a permutation. A permutation is an ordered arrangement. So this ordering is really, really important. Okay? That's going to be one of the questions, because of course we're going to look on the flip side as well when the order doesn't matter anymore, right? But those are just combinations. So in a test situation or an assignment, one of the key things that you're going to have to ask yourself is, does order matter, right? And so, and that's going to set you down the right path. Okay. So an ordered arrangement of k elements selected from a set of n elements where k is somewhere between 0 and n, it's allowed to be n, right? That's a subset. It's the improper subset, but still. Where no 2 elements of the arrangement are the same. Okay, that's also important. It's called a permutation of n objects taken k at a time. Okay. Now, we're only given the notation for it, but don't worry, it's down here. So the total number of such permutations is denoted by the permutations of n. I want to say choose K, but it's not choose K, taken K at a time. So you've got this P function, and most calculators, or at least mine, uses, where is it? NPR, I think. Ooh, it's been a while. There. Or on your calculator, you might have something that says NPR. Any scientific, I'm going to go out on scientific calculator has this permutation button. Okay. And so N is the possible elements and R is the size of the subset. Okay. Just like N and K. So N is generic and R or K or whatever is interchangeable. Okay. So are we ready for theorem? That's important. Uh-oh. Permutation counting formula. The number of possible permutations of K elements taken from a set of N elements is this PNK. And it starts off, of course, the same way as if we were rearranging all the elements, right? We still start off with N options, N minus 1 options, N minus 2 options. But then we're not rearranging all of them, right? Just K of them. Okay? And so here we end when we say N minus K plus 1. Why? Why is it N minus K plus 1? Because I want, well, I guess it's hard to, I think the easiest way would be to do an example with values of N and K. Because it's hard to see. So what I'm struggling with here is it's hard to see why you should end at N minus K plus 1. But maybe you're the type of person where it just makes sense to you. I don't know. But it's because we start at N and we want to go to K elements. Or K, I'll just say K. Let's confirm. Let N be 10 elements, and I'm gonna do 4. Let K and K is equal to 4. Really hoping this works out. I haven't, let's see. So then N is 10. 1, 2, 3, 4. Because I'm forcing K to be 4. Then I have 9 options, then I have 8 options, and then I have 7 options. And I really hope 10 minus 4 plus 1. Phew. Oh my gosh. Can you imagine if that hadn't worked out? Oh, what a relief. It's not a proof, but it's evidence that it works. They do the proof, but like I said, that's not what this is about. We have to be able to answer questions and read questions and kind of apply the formulas for this section. But feels good to have pseudo confirmed this last term, right? And so I'm sure there's a fancier way to do it. But whenever I'm not sure, right, I just do a simple, a minimal working example, right? Which you probably have worked with, right? You have to kind of boil down your question to the minimum working parts. So by letting n be 10 and k be 4, we can confirm things. Or whatever easy numbers you want to deal with. So what that means is, okay, so I can have n times n minus 1 times n minus 2. So far, this is looking like n factorial, right? The problem being we chop it off at n minus k plus 1, right? And so this is the same as saying, okay, that's n factorial divided by n minus k factorial, because why? We have n factorial, but then I want to chop it off at n minus k plus 1. Oops. Let's see here. It's sloppy, but I think I might do something like this, n minus 2 dot 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 to n minus k. No, I'm ditching this. Sorry. I stuck with it the last time. You can break up the factorial, but the math's not coming to me. Well, sort of. What happens is n factorial, it's going to be easier if we approach it from this side instead. Okay, n factorial, so that's where I'm changing course to. N factorial divided by n minus k factorial looks like this. Oops. Bracket on the other side. How about that? Well, that's the same as n times n minus 1 times n minus 2. See, I would have got there eventually. N minus k factorial. Oh, I need more room. This is crazy. Oh, I have more room. I need more room. N minus k. What comes before n minus k? Well, n minus k plus 1 times n minus k factorial divided by n minus k factorial. That's how this multiplication becomes this in terms of factorials, right? Like I said, most calculators are just going to do this for you, right? But if you had to, in a pinch, you could rely on the formula, the factor with just the factorials, right? But the key thing is to remember that you're finding the number of permutations, meaning order matters, from a set of n possible outcomes and k elements from those n. This is what I was trying to reverse engineer and it wasn't coming to me. Can you blame me? Plus 1, but it's bigger. Oh, maybe you can. Okay. What if we have just 5 digits, 1, 2, 3, 4, 5? Okay. A couple of different problems. And the reason I like this one is to highlight the subtle differences in the questions that are going to give you different results, okay? And expecting different answers, right? And what's also nice is they show you 2 different ways of solving it. I'm sure if you were really hard pressed, you could find a third solution, right, to get to the same answer. And so that's part of the problem with this stuff is there's so many ways to get there, right? But they're giving us 2, so that's nice. As long as one of those ways makes sense to you, then you've got it, right? So it's nice to see the different ways that you could solve it, right? But at the end of the day, you only need one. So one thing that I encourage you to think about is which one, so without kind of looking at the answers, which one does your brain do naturally, right? Where does your brain go? And then you follow your brain. Haha. How many 3-digit numbers can be formed if no repetition of digits can occur? Who sings like that? Someone famous. Is it Nicki Minaj? Whenever I say occur, it makes me think of that. Anyways. How would you solve this first one? We only have 5 elements to choose from, right? And so how many 3-digit numbers? Well, in terms of my trusty slots, right? I have 3 slots to fill because I'm looking for 3 digits. And no repetition, none. First slot, I have all 5 to choose from. Right. Second slot, well, I've already used one, so I'm not allowed to use it again. So now I'm down to 4 options. Third slot, now I'm down to 3 options. And if I multiply those through, I get, now I have to cheat, 60. It's down below. All right. That's how my brain approaches it the best, right? And the other solution, a little bit more sophisticated, I guess, is using the permutation formula, right? Permutations, order matters, no repetition. And so here we've got 5. So n is 5, and I'm wanting to select 3 of those. So then I can use that permutation formula or your calculator, either way, and find that the answer is still 60, which is a relief. Right? So 2 different ways of doing it. I would say for me, the first one is kind of more intuitive. Right? But maybe like the permutation formula, who knows? How many 3-digit numbers can be formed if repetition of digits is allowed? Again, I use my trusty slots. 1, 2, 3. But now what? Now I can have repetition. So I have 5 options, and then I have 5 options again, and then I have 5 options again. That's nice. Lots of options. So here the key is repetition is allowed. And I have to steal 125. Good thing I've got my cheat sheet lower down. we can't use the permutation formula, right? Because we have to have unique elements, right? Once I've used it, I can't use it again. So the whole repetition is allowed, puts a stop to that, right? And so there's only one given solution to B, but I'm okay with that. My way worked, so that's good. Maybe that's why I like it, because it works almost every time. And for what we're doing, it's going to work every time. So oh, give you the solution. I want the question. How many 3-digit numbers can be formed if only non-consecutive repetition of digits is allowed? Trust the slots. Okay. If I'm allowed repetition, but only non-consecutive repetition, what does that look like in terms of options? For option 1, I have all 5, right? For option 2, it doesn't matter what I used here, but I'm not allowed to use it again, right? Which means I have what? I have 4 options here, right? Same thing here. I'm not allowed to repeat the number I had here, but I am allowed to repeat the number I had here. So it's kind of, I'm down 1, but then I'm up 1, right? And so this is also 4, which, who knows what that is? 80. She says, surprised. Question?
Yeah, I'm sorry, I'm just kind of confused. So it's like we're down 1 and we're up 1 for 4 again. How do we do that?
So yeah, so the key is we're allowed repetition as long as it's non-consecutive. So I can't have things like 1, 1, 2, but I'm allowed to have 1, 2, 1.
Oh, okay.
Right? And so the first one is free and easy. I'm allowed to do whatever I want. But then once I've used that as my first number, I'm not allowed to use it as the second number.
Oh.
But then once I'm here, I'm not allowed to use the previous number, which would put me down to 3, but I am, so the first number is back in play.
Yeah.
Adding it up to 4. So it's kind of like, yeah. This one's kind of a little bit of a trickster, right? But if you think about it a little bit, and I mean, however you want to visualize it, right? I think visualizing it helps me. All right, so here, non-consecutive repetition is allowed. But I don't think they gave, no, only one solution. Some exercises on permutations. Right. Here's some more that you can practice with, right? I'm saving them for Friday, but 3-digit numbers again. Stretching the mind a little bit. How many of these are even numbers? How many are greater than 250? That kind of thing. What? Crazy. If I asked you to, well, first up, are there any questions? Are we a keep going bunch, or are you a take a break bunch? I can't tell. I never give breaks, so I had a summer class for 3.5 hours one time and I didn't give them any breaks. So it wasn't on purpose, but I got really into it and no one said anything. And that's weird, right? But so if you want to break collectively, say so now. I cannot read you guys. Then we get to go 10 minutes early, at least. How about that? It's the worst when I give a break and then we're done like 15 minutes later. That's no fun. That's a waste of time. So give it a stretch. Well, let's keep going. If I asked you, and you're welcome to stretch and stand up and do whatever you want, I'll keep going. But I get to move around the whole time. So it's pretty unfair. If I asked you to count how many people are in the room, think about how you would do that, right? Are you counting by ones? That's separating everyone into one, right? How would I do it? I count by twos because I worked at a daycare for many summers in a row, and you're constantly counting kids, 2, 4, 6, 8, 10. So I can count, not to brag or anything, but I can count by twos really fast. Yeah, we're down one. And you always know which kid it is. It's missing. But anyway, so what if you're really bold? Groups of 4, right? I'm making groups of 4 and counting those groups of 4. That's crazy. I can't do that. Or it would take me longer than going by twos, right? What are we doing? We're partitioning, right? We are assuming that everyone just sits in one spot, right? If people are moving around, then it's harder. Take it from me, right? But in this scenario, right, we've got options. But what we're doing is we're taking the set of people in this room and we're partitioning them into disjoint sets, right? You can't be in this count of 2 as well as this count of 2, right? That doesn't make sense. Then I'm not counting properly. That's just weird, right? And so we do that a lot for counting, is just partitioning the set, and it makes it easier to count things, right? And so let's talk about, in terms of set notation, what is a partition? A partition of some set A is a set of one or more non-empty subsets of A, okay, where every element is in exactly one of these subsets. Okay? Whether that be groups of 1, groups of 2, groups of 3, groups of 4, it doesn't matter, right? But you're not going to double count people in those groups. And so what happens is the union of all these subsets makes up the entire full set, right, of A. Yeah.
This question, yeah, like from chapter 1, like I was kind of confused, like U and the upside U's, like what is that again?
So U is the union, which you're going to read as or. And the intersection, well, the upside down U is the intersection, which you're going to read as and.
Oh.
As long as we're not talking about the same set, right? That's all this is saying. If I is not equal to j, right, then a subscript I and a subscript j is the empty set, right? Just by definition, because we can't have elements in 2 of these subsets at the same time. Okay. And so then I'll start AI and AJ J are disjoint, which we saw last day. Right. No elements in the shared set. Whoa. Someone's done with this day. So in terms of terminology, the subsets in a partition are often called blocks. Okay? And so we can partition sets into blocks. We can talk about blocks. And this definition, notice how it keeps going here. We can have infinite subsets because we can deal with infinite sets. That's not something that we're going to need to think about too much, but if A is finite, then the number of subsets can be no larger than the cardinality of A. Why is that? Right? The smallest way that you could, I guess, partition the class here is by ones, right? You're in a set, 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 you're in a set. When do I stop? You're in a set, you're in a set, you're in a set. You get a set, you get a set. Everyone gets a set, right? But so if you have a finite set, then the number of subsets that you can partition it into, notice that we're not talking about power sets or subsets or anything like that. We're talking about partitions. So the smallest number of, the largest number of subsets that we can have or partitions is the cardinality of A. Okay, so let's see here. I'll write it on the side. The largest number of possible partitions of A is the cardinality of A, of course, assuming that it's finite, right? If each element is its own partition. That's all that's saying. Can take it back to sets, but there are some better ones that I'm saving for later. But we can talk about integers mostly because I want you to remember that the set of integers, right? Fancy Z is the set, oops. Let's just do this, is the set from negative infinity, oh, not inclusive, to positive infinity. All right. So integers are whole numbers. All right. How can we break up, if we think about this number line from negative infinity to positive infinity, what are some of the ways that I could break them up, right? I would argue infinite ways, right? There's so many different ways that I can slice and dice these, right? The set of integers, but two possible ways are the set of individual n's, right? I name every single element in the set of integers. It's impossible, it's infinite, right? But that's true, that is a partition. Not very helpful for counting, but still. What if I broke it up, right? What if I said, okay, n is, so overall it's a set, right? But also n is in the set of integers such that n is less than 0, not including 0, because then I put 0 on its own. So got a special set. And then I said, okay, the set of integers such that n is greater than 0, right? Now I've just chopped it up at 0, right? You guys go in one set, 0 goes in one set, and you guys go in another set, right? The only difference here, at first I thought, wait, what are you saying? You just said that this is a possible partition, but they've changed the inequality to include equal to 0, and that's why it can't be a partition, because here it includes 0 and here it includes 0, and that's not allowed, right? They have to be disjoint. And again, if you have some blocks that are empty, that's bad. Right, why is it empty? N is in the set of integers such that the absolute value of n is equal to k, such that k is -1, 0, 1, 2, 3, blah, 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 blah. But if I take the absolute value of any number, I'll never get to -1. So I've never defined that subset or that partition. So what we have, right, is kind of similar to the cardinality of the Cartesian product. But if we have partitioned A into all these little subsets, then what can we do? Well, I can find the size of the subsets, right? And then I can add them up and find the cardinality of A. You know? Whenever you see this, the union, I read it as or, but in my mind, I also think addition, whereas and is going to be multiplication. Okay. Maybe I'll add that to the note I wrote earlier. So or it tends to be addition, right? This or that, or that, or that. You're adding them all up. Whereas the intersection or the and tends to be multiplication. I'm grabbing a sandwich and a beverage. All of a sudden, I'm multiplying. So counting in disjoint or counting disjoint subsets is very easy, right? We just figure out how many are in each subset, add them up, and then there you have it, right? So the sophomore computer science majors were told they must take one and only one of the following courses that are open only to them: cryptography, data structures, or JavaScript. Sounds like courses we have. The numbers in each course, respectively, for sophomores, computer science majors, were 75, 60, and 55. From there, how many computer science majors are there? So now they were told they have to take one, but only one. So we're guaranteed that each student is in one of these. So what can we do? I can just add up the numbers and find that there are 190 computer science majors. Oh. That's easy enough. Problem is, if we have something like the next one, it was determined that all junior computer science majors take at least one of the following courses: algorithms, logic design, and compiler construction. Assume the number in each course was 75, 60, and 55, respectively, for the courses listed. So far, similar numbers, right? But further investigation indicated 10 juniors took all 3 courses. Oh my gosh, crazy. 25 took algorithms and logic design, and 12 took algorithms and compiler construction. And 15 took logic design and compiler construction. So how now knowing that, right, we've got a lot of overlap, right? Potentially 3 overlaps. There were some students that took all 3, right? And so now how do we count? I'd say the easiest way to count these is by using a Venn diagram. What would that look like? You've got 1, 2, 3 things that we're talking about. And don't worry, they've done a beautiful one here, but I want to get there together. And I'm going to label these A for algorithms, L for logic design, and C for compiler construction. Now, we know that this total circle is 75. I'm not going to jot that down right away because how I want you to approach these Venn diagrams is to start in the very middle, right, and work your way out, right? Because then you can deduct the numbers as you go. So we're going to start here. What's the number that goes here? It's all 3, right? They took all 3. How many were there? 10 juniors took all 3 classes. That's your first thing that you're going to do, right? Start in the very, very center. 25 took algorithms and logic design, which is going to be what? That's going to be this intersection. Now, we already have 10 of those on the board. So we have to take that out to fill this region, right? The total here is 25. But to fill this region here, I have 15. 25 minus 10. Gonna run out of colors. 12 took algorithms and compiler construction, but 10 of those were taking all 3, right? And so there are 2 of them that only took the 2. So notice the terminology, right? If you only took algorithms and whatever it is, compilers, construction, but it doesn't say that. It just says it took both, right? And then 15, this is step 3. 15 of them took logic design and compiler construction, which puts me at 5 here, right? 10 and 5. And again, I just want to highlight that it's just these little regions. But notice how we're making puzzle pieces, and then you'll be able to use those partitions to add things up that satisfy some criteria. All right. And now there were a total of 75 in the entire A circle, right? And so now here I have 75 minus 15 minus 10 minus 2. I'm not getting there. 60, 50, 48. Oh, all right. 75 minus 15 minus 10 minus 2. I did it. 48. Right? Because the total A circle has to be 75. Right? That's the tricky part. It's kind of pulling out the duplicates and then making sure that it's all In my mind, I think of it as smooth, right? You can't be double counting in here, right? Same thing for the logic. We had 60 minus 15 minus 10 minus 5. I'm getting 30. But remember, this 30 is just this kind of half moon of the L that only took logic design, right? And then finally, 55 minus 2 minus 10 minus 5. $38. So now what? Now, as long as you use these values, right, not the overall values, then you can just add these all up, right? And in your mind, what you're actually doing is you're saying, I'm going to add up the students who took only the algorithms course or algorithms and logic only, or all three, right? Or only logic, right? Whenever you're saying or, you're adding. Okay? And I don't have the number. 48 plus 15 plus 10 plus 30 plus 2. I jumped around, plus 5 plus 38. I get 148 computer science majors. Hopefully that's right. I do not feel like oh, I thought those were numbers. They're just referring to the regions. It's like, that's not at all what we just did. They're finding the regions because they don't have that much space. Let's think about another way that you could solve this. What if I wanted to use these overall numbers, 75 and 60 and 55? What would I have to do? I'd have to, right here, there's overlap. If we just focus on 2 for a second, 2 sets, right? There's overlap, so I'd have to subtract the overlap once, right? But now I have to subtract the overlap twice, but then I've subtracted too much and I have to put it back in. So it's a little bit more advanced than just the 2 sets. But what happens is it ends up looking something like this. We have some partitions, right? A1, A2, A3. And what I want to do is I want to find the size of those. Those are the initially given numbers. And then I subtract the repeats. That's the other way to do it. I subtract the repeats and then add them up because it makes more sense to me. But yeah. So in terms of formulas, right, it looks like this. We take the size of each of the sets individually and then subtract the overlap is all this is doing. Subtract the overlap. If you have 3 sets, and obviously you can keep going, but it changes a little bit, okay, then you can add up the general cardinalities, but you have to subtract the overlaps. But then, like I said, you end up subtracting the piece in the middle completely. So then you have to put it back in, right? Because you want a smooth field. Okay. this is something that you need to be able to use, but if you can look at the Venn diagram and figure out from the Venn diagram, then that's totally fine. That's counting too. A couple exercises. Okay. Combinations. I'm going to jump ahead to talk about the permutations versus combinations. Like I was saying before, order is important in permutations, but order is not important in combinations. And so that's the distinction between the two. But otherwise, they're very similar. So, there's one I wanted to do. I think it's this one. We can talk about the permutations first, though. So if we have a set of 4 letters, A, B, C, D, okay, then how many different ways? Whoa. Oh my gosh. It actually bumped me back there. That's pretty cool, but it's not what I wanted. Oh boy. Scrolling. Oh, okay, getting warmer. Okay, I'm gonna try to not hit this link. So if we have 4 elements and we want to think about how many different ways I can permute 3 of those, right? Then I can use the permutation formula and find that there are 24 different orderings of 3 letters from a set of 4 letters, which is A. Okay. But the one that I am most interested in is example 2.4.2, mostly because we did it last day, right? It was very tedious. We didn't even do it together because I didn't want to write it out again, right? But when we had a set of 4 elements and we were trying to figure out how many different sets of 3 elements could I make, how many different subsets, and now we're revisiting that. Okay, so we want to, how many ways can we select a set of 3 letters from A, B, C, D? We're not concerned with the order of the 3 letters, just like in any set, the order doesn't matter. Okay. But we can't have A and A because that just makes A, right? And then we're back to 3, or sometimes it reduced to 2, which means it was out. Okay. By trial and error, which is how I brute forced it, we get ABC, ABD, ACD, and BCD, and they're the only listings possible. Okay. What we can do is we can say, okay, what if I kind of introduce this idea of from a set of 4, I'm choosing 3, right? And the order doesn't matter anymore. Okay. And that's where this choose function comes from. Okay. And it's technically called the binomial coefficient. There was even an exercise where you had to expand something with the binomial coefficient, but I said, don't worry about it until next week. And here we are. Blink, and you're here. Okay. So what is it? Well, we still don't know what it is, but we're going to talk about how to read it, I guess. So let n and k be non-negative integers, then the binomial coefficient n choose k, which we kind of write like a fraction, but no line, right? And it's in round brackets, represents the number of combinations of n objects taken k at a time, and is read n choose k. Okay. So in terms of combinations versus permutations, right? Combination ABC, it doesn't matter, order doesn't matter here. In fact, I would say combinations up top versus permutations, just to illustrate that, well, all these lump into one set of combinations, right? So that's the difference. Let's leave that, and I just want to jump right to what it is. So from a set of n elements, we're choosing k of those. And the formula involves the factorial again, n factorial over n minus k factorial times k factorial. That's weird, but it's true. Okay. We're going to ignore the proof because that's just how I roll. Okay. But take it as a fact. There is a choose function on most scientific calculators. Oh, if you have the p function, you have the c function, right? And so n, c, r on your calculator. You can play around with how to use it on your calculator so you don't have to use the factorial. Okay. Okay, fine. Now I promised that we would end early. I'm feeling some pressure here. Let me see. Okay, not bad. I'll do the last one on Friday, how about? If you're flipping a coin, for example, and you flip it 5 times, how many ways can 3 heads be obtained? Again, we could list all the possible ways that could happen, right? But the 3 heads, you could have head, tail, tail, head, tail. Think of all the different ways, but what am I doing in my mind? I'm doing 1, 2, 3, 4, 5 times, right? This could be a head, this could be a tail, head, 3 heads. So that's a tail. That's just one of the possible combinations. An obvious one would be head, tail, tail, right? Those are different from each other, right? There are 3 heads regardless, so the probability of heads, now we're told that it's a fair coin, so 50-50, right? So it's not that interesting to write out. But 3 heads, 2 tails, regardless, and all we're doing is we're shaking it up, right? And so what we have is we have 5 flips, each an opportunity to get ahead. And what we're saying is, how many ways could I get exactly 3 heads, right? And it doesn't matter where they appear. I just want to know how many ways, how many of these different permutations can I get, right? And so that's where the 5 choose 3 comes in, which if you work out with the factorial, it turns into 10, right? Or if you use your choose function on your calculator, the key is to recognize that the order doesn't matter anymore, right? But you're counting the number of permutations. Okay, step away from the plate. I promise to let you go early. I know it's not even that early. All right, okay. I'll stop there. I'll pick it up on Friday, I guess. It feels so far, but I'll stop the recording here.